learners. I am Palak Gupta, and in today's session we are going to dive deep into an essential memory management technique, that is segmentation. Before we talk about segmentation, let's quickly understand the bigger picture, memory management. It's a key function of the operating system responsible for allocating memory to processes, ensuring protection and improving system performance. There are three major memory management strategies: contiguous allocation, paging, and segmentation. Contiguous allocation is simple but suffers from external fragmentation. On the other hand, paging, which divides memory into fixed size pages and avoids external fragmentation but causes internal fragmentation. And segmentation, our main topic for today. It maps memory to local program like units like code, data, or stack. Now, what is segmentation? Segmentation is a logical way to divide memory. Instead of fixed size blocks like paging, segmentation divides memory into variable sized segments, each representing a logical unit, such as code, data, stack, heap, functions, arrays. These segments reflect how programmers naturally structure code, making it easier to manage. Analogy: book and chapters. Imagine a program is like a book. Each chapter is a segment with its own length. A table of contents lets you jump to the exact chapter, just like a segment table lets the OS jump to any segment directly. So you don't flip through every page, you jump straight where needed. In segmentation, a memory address has two parts: segment number, which identifies the segment, and offset, the distance from the start of that segment. Every process has a segment table with a base address where the segment starts in memory and a limit, the length of the segment. This keeps each segment isolated and protected. Now the question arises, why use segmentation? Let's explore why segmentation is so useful in an operating system. First is modularity. You can divide large code bases into modules. Each segment is like a module independently compiled, loaded, and debugged. Moving further, we get the protection. Each segment has its own access rights: read, write, or execute. This protects against memory corruption and buffer overflows. Moving further, we have sharing. Common segments like libraries can be shared among processes without duplicating memory. And last, growth flexibility. Stack and heap grow in opposite directions, and segmentation allows them to grow independently. Now let's discuss the advantages of segmentation, which are logical view of memory, better code organization, access rights per segment, code or data sharing, stack and heap grow independently, faster context switching, only the segment table needs updating. This makes it perfect for multitasking and secure environments. Disadvantages of segmentation. Here we can see segmentation is not perfect. It comes with some challenges, which are external fragmentation. Free memory gets scattered. Complex allocation, which needs algorithms like best fit or first fit. Address translation overhead. Converting logical to physical addresses takes time. Not widely used alone. Modern OS often combine it with paging. Complex permission management. Managing access rights across many segments can be hard. Now, let's take a moment to compare segmentation and paging side by side. This table helps us understand the key differences between two memory management techniques. Let's go row by row. Division. Segmentation divides memory based on logical structure of a program. So things like function, variables, code, data, and stack each get their own segment. On the other hand, paging ignores program structure and just splits memory into fixed size blocks called pages and frames. Moving further, unit size. In segmentation, the segments are variable sized. They grow on or shrink based on the needs of each component. But in paging, every page and frame is the same size, typically 4 KB, which makes management simpler but less flexible. Now, let's take fragmentation. This is important. Segmentation suffers from external fragmentation because variable segment sizes can leave unusable gaps in memory. Paging, however, causes internal fragmentation since fixed size pages might not be fully used, leaving unused bytes inside. Next is addressing. In segmentation, the address is made up for a segment number and an offset. In paging, it's a page number and offset. Similar structure, but the interpretation is different. One is logical and the other is physical. Next is view of memory. Segmentation reflects the programmer's view. They think in terms of modules or section. Paging reflects the system's view. Memory is uniform and divided strictly for efficiency. Moving further, we have ease of sharing. With segmentation, it's easy to share specific segments like code or libraries between processes. In paging, sharing is possible but more complex and less flexible due to uniform structure. Moving further, we have protection. In segmentation, protection can be applied per segment, like making code read only or stack non-executable. In paging, protection is uniform per page and may not always reflect logical divisions. Next we have is hardware support. Segmentation needs a segment table and each segment must store a base and limit. Paging needs a page table which maps page number to frame numbers. Usage. The segmentation is best used when logical structure of a program matters. For example, separating code from the data. Paging is more common in modern operating systems because it's simple, efficient, and works well with virtual memory. So the bottom line is segmentation is programmer friendly, logical, and modular. Paging is system friendly, uniform, and efficient. Most modern OS like Linux or Windows combine both to get the best of both worlds. Segmentation for logical memory organization and paging for physical memory efficiency. Now let's explore the segmented memory layout, a visual way to understand how memory is organized when using segmentation. In segmentation, memory is divided into logical segments like code segment, data segment, heap segment, and stack segment. Code segment stores the actual instructions. It's usually read-only and can be shared across processes. Data segments holds global and static variables. It's writable and may grow as variables are used. Heap segment used for dynamic memory allocation. It grows upwards during execution as the program requests memory. Stack segment manages function calls and local variables. It grows downward as functions are called, especially with recursion. A key point here is that heap and stack grow towards each other, as the OS needs to manage them carefully to avoid overlap. Each segment is independent, has its own size, and it's tracked by segment table, which stores its base address and limit. Unlike paging, these segments are not fixed in size. They reflect the logical structure of your program, making segmentation more intuitive and flexible for modular programs. So this layout supports protection, flexibility, and clear memory organization, just like how we structure our programs in real life. Now let's look at some real-life use cases where segmentation is actually applied. Although pure segmentation isn't commonly used in modern systems by itself, its concepts still play a vital role in various technologies. Let's go over the three important use cases. First is Intel 8086 or 802086 architecture. Used segment registers like CS, DS, SS, and ES. Memory are addressed using segmentation offset, allowing access up to 1 MB. Its key benefit is extended addressability and structured memory layout. Up next is multitasking operating systems. Each process has its own code, data, and stack segments. Ensures isolation and protection between processes, allowing stack and heap to grow independently. Its key benefit is for better memory safety and support for multitasking. Next is compilers and run systems. Programs are divided into text, data, BSS, stack, and heap segments. Access rights are enforced for each, helping catch segmentation faults. Its key benefit is memory safety and efficient runtime memory management. So, while modern systems often use segmentation with paging, segmentation still plays a vital role in memory structure, protection, and modularity. To wrap up, segmentation provides a logical and structured way to manage memory. It divides a program into segments like code, data, and stack, reflecting how programs are actually written. This makes memory easier to manage and protect. Each segment is independent, can have its own access rights, and help prevent issues like buffer overflows and unauthorized access. Especially important in multitasking environments. However, segmentation can cause external fragmentation which affects memory efficiency. That's why most modern operating systems use a hybrid approach, combining segmentation for logical structure and paging for efficient physical memory management. In short, segmentation is a key concept that supports safer, modular, and more organized program execution. For further reading, you can refer to Operating System Concepts by Silberschatz and Galvin, Modern Operating Systems by Andrew Tannenbaum, and of course your class notes like this one. That brings us to the end of our session on segmentation in operating systems. Thank you so much for watching.